Okay, we're starting with Chapter 8, Chemical Reactions. The big piece of this chapter is that we're going to be able to identify what sort of chemical reactions we're dealing with, and from that be able to predict what the products of that will be. Very, very important, very nice piece of chemistry. So really pay attention to patterns, especially patterns amongst the reactants. That's going to be our kind of big piece moving forward. So a lot of Section 8.1 is kind of a recover of what we covered back in Chapter 2. So just bear with me. So whenever we say the word chemical change or chemical reaction, they are referring to exactly the same thing. Again, what we're seeing here is one substance is turning into another. And we're breaking old bonds, we're forming new ones. That's a chemical change. That's a chemical reaction. And again, we saw this back in Chapter 2, but just wanted to give us a refresher of that. Now, what's happening in a chemical reaction? So Dalton actually did a good job explaining this. So as reactants are turned into products, the bonds that hold the chemical reactants together break apart. We have to break apart those initial bonds, then new bonds are formed. Think of it kind of like building a structure out of Legos when you have a limited supply. If you have a Lego house built and you want a Lego car, you have to break apart the bricks from one another, break it down to its components, and then rebuild into the shape that you want. Very, very similar to what's happening in a chemical reaction. There's no new atoms brought into the mix. No matter is created or destroyed, so this goes back to our conservation of mass. Elements stay what they are. We're just rearranging what's present. So one of the first ways to look at what's going on in a chemical reaction is to focus on what's called a word equation. And it's just a shorter way of writing down a description of a chemical reaction. Simply put, we write down the names of the reactants on the left, the products on the right, and we separate them with that right-facing yield arrow. If we have multiple products or reactants, we separate them with a plus sign. Again, we want to think of that plus sign serving the same role that a space does in a sentence. That space separates one word from another. The plus separates one substance from another. So a quick example of this, so this is a description of a chemical reaction. Pure copper can be produced by heating copper 2 sulfide with oxygen. Sulfur dioxide is also produced. So if we want to make a word equation out of that, one of the first things we want to do is figure out who the reactants and the products are. So that would be the copper 2 sulfide and the oxygen. We look at who the products are. That would be the copper and the sulfur dioxide. And we put the reactants on the left, products on the right. So that is shorter than what we see up front. Much better, much shorter. Now we want to transition from the word equation into actual chemical equations. Because word equation works, but they're still too cumbersome, we can be more efficient about this. So the only difference between a word equation and a chemical equation is instead of writing down the name of the substances, we are writing down the formula for it. So this is where we go back to writing and reading chemical formulas from previous chapters. And again, we're using chemical formulas. So a quick example of this. So with the previous example, we had copper 2 sulfide and oxygen reacting to produce copper and sulfur dioxide. So the formula is involved. Copper 2 sulfide is CuS. Now remember the reason that this is the way that it is. Sulfide always has a 2 negative charge. And it says it's copper 2 sulfide, so that 2 is telling us that the copper has a 2 plus charge. So we need one of each to give us a neutral compound. Oxygen is diatomic. It's in its elemental state, so O2. Copper is just Cu, that's in its elemental state, and sulfur dioxide, again, sulfur dioxide, dioxide means 2 oxygens. So the kind of equation for this simply would be what you see there below. And again, we like it even shorter than a word equation. Now what we just made is what's called a skeleton equation. And in a skeleton equation, we're not concerned with the amounts of the products and reactants. We're just saying this is what's there. We're actually going to look at how to change this in upcoming sections. But for today, skeleton equations work pretty well. They just tell us, again, these are our reactants, these are our products in a short, concise way. Now, what we also want to get in the habit of is writing down the physical state of each substance. That's going to come in handy later this chapter. We put, after any substance that's a solid, we put an S in parentheses, AQ meaning dissolved in water or aqueous, G for gas, and L for liquid. Very, very important that you get in the habit of that whenever you can. So, for example, if this was our reaction, again, this is just a skeleton equation, so we don't have to worry about how much of each chemical there is. So this would tell me that solid iron and the iron 3 oxide were solids, oxygen was a gas because that's the symbol they have after them. A couple more symbols that you'll see. There's a full list on page 206 of your textbook, but I'm going to cover the big ones. If above your yield arrow they write the formula of a compound, not the word formula, but they would write the formula of a compound above the yield arrow, that means that a catalyst was used. And this is my really worst science joke of the year. A catalyst is not a bovine directory. What is it? It is a substance that speeds up a chemical reaction without being used up. It is not considered to be either a reactant or a product, which is why it's above the yield arrow. As we move forward in chemistry, we'll learn why catalysts do that and how they work. So for example, if oxygen was a catalyst in a reaction, we would put O2, or even the word oxygen above the yield arrow. And finally, just a few more symbols. Both of these mean the same thing. If we put the delta sign, we want to be very careful we put a delta and not a triangle. Put a delta sign above the yield arrow, or the word heat. Both of those are indicating that heat was supplied to the reaction. They are not a catalyst. They are not a chemical. Now that being said, this is very rarely enforced in most chemical reactions. You might see it once or twice, but for the most part, it's not present. So you don't have to worry about it very much, if at all. Okay, we are now going to be transitioning from the skeleton equation to something that does care about the amount of matter that we deal with, that we have. And again, we have to obey the law of conservation of mass. That's the law. And again, this tells us that we cannot gain or lose mass. Now, previously, we've said that this means that the mass of products equals the mass of reactants. And that's a good starting way to look at this in chemistry. But what it also means, so this is not replacing what we said before, it's adding to, that the atoms present in the products must be the same atoms present in reactants. Because again, atoms do not change from one type to another during a chemical reaction. They just rearrange. And again, what we're going to see here is that balancing equations is going to fix skeleton equations so that they follow this rule. So, in a balanced equation, it's going to be an equation where each side of the equation, meaning products and reactants, has the same number of atoms of each element. And also it's one that will obey the law of conservation of mass. Now, sometimes we're lucky, and when we are given a chemical equation, it might already be balanced. So take a look at this equation here. We have solid carbon reacts with oxygen gas to make carbon dioxide. Now, one of the things that we can look at this is that if we look at the reactants and look at the products element by element, currently we see we have one atom of carbon in the reactants and 2 atoms of oxygen in the reactants. Likewise, we have 1 atom of carbon in the products, 2 atoms of oxygen in the products. So that means it's already balanced. Happy day. Don't have to do any work with it. But that's a rare case. More often we see something like this, where if we look at this, we can see that on the reactant side there's 2 hydrogens. Products also have 2 hydrogens. It's a good start. We see 2 oxygens on the reactants, but only 1 oxygen on the products. So this equation is not balanced. It would be a fine skeleton equation just saying hydrogen and oxygen react to make water, but not a good balanced equation. So to balance an equation, we're going to use coefficients. And a coefficient, like in your math class, is a whole number that's going to appear in front of a chemical formula. Now in your math class, a coefficient might have been, let's say I had a term that said 5x squared. The 5 would be your coefficient. And if you think in math, if I say 5x squared, what does the 5 tell us? Well, it tells us that we have 5 of the x squareds. In a chemical equation, it plays the exact same role. The coefficient tells us how many molecules, atoms, formula units, moles, whatever are necessary for that reaction to be balanced. So for instance, if during looking at a chemical equation I saw 3 H2O, I would know that for that reaction to be balanced, I need 3 water molecules. Also, like in math, no coefficient shown indicates a coefficient of 1. Again, in math class, you don't write 1x, you just write x. So if it has a coefficient of 1, you don't have to write it. Writing it isn't wrong, just not necessary. And again, you cannot change subscripts. We can change coefficients, and that's it. So when we're balancing the equation, we cannot change subscripts. Changing the subscript changes the substances that we're dealing with. And that's not what's happening. We're not changing what's there when we're balancing. We're just showing that we're obeying the law of conservation of mass. So, rules for balancing equations. First thing you need to do is make sure that you have all the right formulas for the reactants and products. Should go without saying, but if you have a bad formula, you're going to have bad balancing time. Write down the skeleton equation. Oftentimes, if it's just a balancing equation problem, this is where you start. Then you're going to count up how many of each atom there are for each element in the products and reactants. And what I like to do is make a little table underneath the equation that says, okay, if it has sulfur, I write an S, and then I write how many sulfur atoms there are. If there's oxygen, I write an O, then I write down how many oxygen atoms there are. So you're going to count up the number of each atom of each element within your reactants, then mirror the element list on the products and tally up how many of each element you have there. Now, here's just a piece of advice. Doesn't have to be followed, but makes things a little bit easier. If you have the same polyatomic ion appearing on both sides of the equation, keep it together. Don't break it apart. So if you see sulfate appearing on both sides of the equation, keep sulfate together as SO4. You don't have to. You could break a sulfate up into a sulfur and oxygens, but keeping the polyatomic together often saves you some grief. And then you're going to balance the elements one at a time using coefficients. Remembering that if you put a coefficient in front of a substance, it's going to multiply everything in there by that coefficient. So for instance, if in a water molecule, water being H2O, if I put the coefficient of 3 in front of it, meaning 3 water molecules, that would be a total of 6 hydrogens and 3 oxygens. And it's not uncommon when you're balancing to have something that starts balanced, you put a coefficient in there and it throws it out of balance, so you're kind of playing catch up. That happens pretty frequently. But again, you can only change the coefficients, not the subscripts. Then just double check that everything is the same on both sides. That's what's nice about mirroring your list between the reactants and products. If it's all the same on both sides, you're balanced, you're good to go. Last little note, please make sure that your coefficients are all in the lowest possible ratio, because they need to be. So if, let's say you have 3 coefficients in a balanced equation and they're all 2, that can be reduced that they'd be the same as them all being 1. Or let's say you have 2 chemicals in an equation, 2 only. One has a coefficient of 4, one has a coefficient of 2. That can be reduced down to 2 and 1. So here's just a piece of advice. Does not need to be followed. This is what I tend to do. This is the order that I balance the coefficients in. I only do this because if I follow this order, I tend to take care of issues before they arise. But if you're not comfortable with this, do what works for you. I call this the MINO method, as in MINO chemistry. Me not know English, MINO chemistry. M stands for metals. Balance your metals first. I is polyatomics, so do those next. N is nonmetals. O is oxygen. H is hydrogen. And again, the reason I like this list is oftentimes by, let's say, balancing metals, polyatomics, then nonmetals, oxygen and hydrogen will take care of themselves just as we go. Not required list to do. Don't have to follow this. This is merely a suggestion. As kind of a hint, when you see H2O, you can think of it as HOH. This can be useful if you see water on one side of the equation and a something hydroxide on the other. Treat water as HOH, now it's hydrogen hydroxide. Just makes balancing a little easier sometimes. Finally, if you were in class, we would go through examples at this point, but due to the technology I have currently, I didn't have a real easy way to put up examples of balancing equations onto this video. So if you are interested in this, please follow the link below. Now I want to note that is not my video. This is it looks like a chemistry teacher by the name of Tyler DeWitt. I found him on YouTube. And his method seems to be very, very similar to what I do. So I thought, why not? And if Tyler, you ever see this, thanks for the good job. So now we're going to be looking at types of chemical reactions. And as we go through this, what you really want to focus on is look at the reactants. Each reaction type has a specific kind of pattern for the reactants, and that's what you want to focus on. So really look at that, look at what the reactants are, and that tells you what the products are. As we go through this, we're going to go through a couple different steps. We're going to complete the reaction after identifying its type. Then, once it's completed, we can balance it. As a note, because this is a common misconception, is that when we are completing the reaction, the subscripts of the reactants and the subscripts of the products can be completely different. So that is true. You might be thinking back to balancing an equation when I said you cannot change the subscripts. You can't change the subscripts when you're balancing. But again, it's a two-step process. You complete so you can change the subscripts in the products, and then you balance where the subscripts have to remain the same. And you'll see how that looks as we work through this. Now the idea behind this and why we want to focus on this is that there are millions of known chemical compounds, lots of different reactions for all of them, and we don't want to have to memorize everything. We want patterns that we can follow, because memorizing millions of things would be dumb. So we don't want to be dumb. We want to be smart about things. So we're focusing on the patterns instead of memorizing each individual piece. And there are 5 broad categories of reactions we're going to study. We're going to see synthesis, also known as combination, decomposition, single replacement, double replacement, and combustion. And we'll look at each of those in order. So combination reactions, also known as a synthesis reaction, it just depends upon your textbook and your chemistry teacher. And in here, what you're going to see is you're going to have multiple reactants forming one single product. Now, if I want you to identify something as a synthesis reaction, what you're going to see are 2 elements in the reactants. It's not always going to be 2 elements in the reactants, but if it's not, they have to tell you it's a synthesis reaction or a combination reaction. If, however, you just see that there's 2 elements in the reactants, assume that it's synthesis. And then what you're doing is you're making a single product. And that product will always be a compound. And we're going to see in a moment, if it's an ionic compound, which is very, very common, you have to make sure the compound's neutral, just like we did back in chapter 6. And again, I'm just trying to drive the point home. One product, and it will be a compound. Always, always, always. And like I said, most commonly the reactants will be 2 elements. Sometimes you'll see 2 compounds, but if you see 2 compounds, they have to tell you it's a synthesis. Otherwise, it could be confused with other things. And this is the general format that we're going to see. We have some substance A reacting with substance B, and we're making one product. One note about that AB, again, the subscripts of AB could be different from the subscripts of A and B individually. Now, if you have a non-transition metal, so that's a representative element metal, and a non-metal, so basically we're having things with consistent charges. The product formed is going to be have our metal cation, non-metal anion, consistent charges. So you want to make sure that your compound is neutral in the end. For example, with potassium here and chloride, I kind of skipped to the end, but we would see potassium plus chlorine, and then what does it make? Well, potassium's a metal, always a +1 charge. Chlorine's a nonmetal, always a -1 charge. So I need one of each, so KCl. Notice that chlorine has a subscript of 2 in the reactants, does not have a subscript of 2 in the products, that's because we're completing the reaction. The compound its formula is whatever it needs to be neutral. So we complete it, then we balance with coefficients. Now, if you have 2 nonmetals reacting, there's lots of different possible products. So for example, if I just say sulfur and oxygen react, we could have sulfur dioxide. We could have sulfur trioxide. You don't know what the product will be without further information. So if I gave you a problem where it was 2 nonmetals, I'm going to have to tell you what the product is. It's the only way you can know. Now, when there's a transition metal and a nonmetal, so remember, transition metals can have variable charges. We can have more than one product possible. So for instance, if I say you have iron and sulfur, you could have this iron 2 sulfide. You could also have this iron 3 sulfide. How do you know? Well, this is another case of I have to tell you. If I just say iron and sulfur, you don't have enough information to determine which compound it's going to be, so you need to be told the name. Then once you know the name, you can write the formula, then you balance. Same steps every time. We complete, then we balance. So we're going to walk through an example. So here is what you could see in a problem. So it just says complete and balance the following reactions. So you see we have calcium and we have oxygen. So I look at this and I go, okay, calcium's a metal, always has a 2+ charge. Oxygen's a nonmetal, always a -2 charge. And I see that I have 2 elements here. Whenever I see just 2 elements, I know it's a synthesis problem. And because it's synthesis, we're going to bring these 2 together. So again, I have calcium with a 2+, oxide with a 2-. So the formula of the compound they will make will just be CaO, because that's what's needed to be a neutral compound, just like we learned back in chapter 6. Now, that's the complete step. Notice again, oxygen on the left has a subscript of a 2. Oxygen on the right does not. That is completely acceptable because the product on the right has the subscripts it needs to be neutral. But we need to balance the equation. And what do we balance with? We balance with coefficients. So then I have 2 calciums, 2 calcium oxides. It's balanced. Everyone's happy. We go home content. Decomposition reactions are going to be our next type of reaction, and they're really the opposite of a synthesis reaction. So what we're going to see is we're going to have one reactant, multiple products. If you see a problem that says complete and balance, and you only see one reactant, you know it's decomposition. Now, again, the reactant will always be a compound. The products can vary. What I want my rule for you to be is if I don't give you any further information, break whatever they give you up into its elements. Now, if I tell you what the products are, use those products. But if I just give you a reactant, a single reactant, and then a yield arrow, break it into its elements, because you really need more information to really go farther with that. So again, here's the general form we're going to see. So we have that compound AB. We're breaking it up into its elements. Pretty straightforward. Most decomposition reactions require energy for this to decompose. Most commonly, heat or electricity is going to be utilized. Here's an example of a decomposition reaction. This is one I would not expect you to know right away. So notice we have a single compound here, that calcium carbonate. And then in this case, I would have to say we form calcium oxide and carbon dioxide. Again, without further information, I would expect you to break it up into its elements. Obviously, that's not what happened here, but further information was provided, and saying it's calcium oxide and carbon dioxide. So we're going to just jump right into an example. So again, complete and balance the following reaction. That's what you'll see very commonly. So I see water there. Water is a compound. I see one compound as our reactants. That tells me this here is a decomposition reaction. If I know that, I know without further information, I'm just going to turn this into its elements, or break this into its elements. So what elements is water composed of? It's composed of oxygen and hydrogen. Notice oxygen and hydrogen both have a subscript of 2. Why is that? Well, it's because oxygen and hydrogen are both one of our diatomic elements. So they exist naturally in their elemental form as a molecule. So again, notice water only has one oxygen. The product's oxygen is O2. The subscripts on the left can be completely different from the subscripts on the right. So we've completed, now we balance using coefficients. It's balanced, we can go home happy. Single replacement reactions are where things start to get a little bit harder. What we're going to see happening here are we're going to have an element and a compound as our reactants. And the element that's by itself is going to try to replace one of the elements in the compound. My very terrible analogy for this is imagine there's a dance. And let's see if I have my form here. So we have this nice couple, B and C, and then along comes A. Dum dum dum. A comes up to the couple B and C. It's like, hey, because that's its name. Hey, how you doing? And C is all aflutter. A and C are now together, and B is alone, sitting by the punch bowl, not crying because B is strong and independent. That's really the single replacement reaction. You have a couple, you have something by itself. The thing by itself replaces one of the pieces in the couple. So again, we start off with an element and a compound. We end up with a different element and a different compound. As a note, the compound that we make here will really always be a ionic compound, so we have to make sure it's neutral. Very, very important. And again, very similar to what we said there. Basically, the metals, if your element is a metal, it will replace metals. If your element is a nonmetal, it will replace nonmetals. Now, metals can replace hydrogen. So if you look at your compound and you don't see any metals present, treat hydrogen as a metal with a +1 charge. We'll kind of see why that is as the year progresses. Now, what's important with this is that there is a metal activity series on page 217 of your textbook. This is not a table you have to memorize. This is not a table you need to put into your notes. This is a table I would provide to you on an opportunity if needed. You can think of this table kind of like a popularity list. It's going to list a whole bunch of elements. If you have an element at the top of the list, think of it as very popular. Anything that's at the top of the list can replace any element below it. But elements at the bottom of the list cannot replace anything above it. So that's the basic rule. So you always have to check that list when you're doing a single replacement reaction. Has to be done. And again, higher things can replace lower things, and you do not have to memorize this. So let's look at an example with this. So replace it with metals. So here's a full thing. So we can see there's our element. Here's our compound. Magnesium is a metal. It's going to try to replace zinc. So what we do is we check that metal activity series. I see that magnesium is above zinc, so magnesium can replace zinc in the compound. Now, to make my compound, magnesium is always a 2+, has a 2+ charge. It's going to be with nitrate. Nitrate is always a 1 negative. So to be neutral, we need 2 of the nitrates. One thing I want to point out, here the nitrate has a subscript of 2, here the nitrate has a subscript of 2. That is a complete coincidence. It is not always going to end up that way. You want to make sure that whatever compound you make is neutral. And then zinc was kicked out, zinc is off by itself, and that's okay. Now, if magnesium tried to replace lithium, so magnesium's our metal, so it's going to replace lithium, which is a metal, nothing happens. Why does nothing happen? Because I check my metal activity series, and lithium is above magnesium, so no reaction. Now, nonmetals, remember, nonmetals can replace nonmetals. Basically, the only nonmetals we're concerned with are the halogen family, fluorine, chlorine, bromine, and iodine. And again, they're all diatomic. And there's no special chart like the metal activity series for nonmetals. Instead, you just look at the periodic table. Fluorine's at the top, iodine's at the bottom. Fluorine can replace any of the others. Iodine can't replace anybody. So, and like chlorine could replace bromine and iodine. So an example with this, so again, complete and balance the following equation. We're going to see zinc and silver. Zinc is above silver on the metal activity series. So here's what they give us. Notice we have an element and we have a compound. Element, compound. So the zinc is going to try to replace the silver. Zinc is above silver on the metal activity series, so this will absolutely go ahead as planned. So the zinc is now going to be at the nitrate, the silver is by itself. Now, when we complete this, notice that nitrate went from having a subscript of 1 to a subscript of 2. Why is that? Well, zinc always has a +2 charge. Nitrate is always a -1. Therefore, we need 2 nitrates to balance out the charge on the zinc. So again, subscripts on the left have nothing to do with the subscripts on the right. And then silver is by itself. Silver is not diatomic, so just Ag. So that's the complete step. And then for balancing, we just use our coefficients. We balance as normal. And double replacement, very similar to single replacement. So if single replacement is a sad event at a school dance, double replacement is kind of like a square dance where you have partners switching. So the way I like to view this is we're going to swap the positive ions within their compound. So you have one ionic compound, you have a second ionic compound, and then they're going to switch to the other one. And we're going to see how that looks. Oftentimes what we're going to see though is with the products, one will be aqueous, the other will be solid, or one will be aqueous and the other is gas. It's actually the production of that solid or gas that really drives this reaction forward and allows it to happen. And we'll take a look at what this looks like on the next slide. So here's an example of a double replacement reaction that's completed for us. Notice I start with 2 ionic compounds. I identify my metals, so sodium, cadmium, that's a cadmium 2 there. I can tell by the charge on the charge because there's 2 nitrates. So they're going to swap with each other, not to each other, with each other. So the sodium will now be with the nitrate, as we see right here. Sodium is a +1, nitrate's a 1-, so we need 1 of each. And the cadmium 2 is going to be with the sulfur. Cadmium 2 has a 2+. Sulfide's a 2-, so 1 of each is needed. Here's another example. Now here's one where we have calcium, and I look over here with HCl, and there's no metal present, but metals can swap with hydrogen. So calcium is now going to be with the chlorine, so we get this calcium chloride. Again, making sure the compound's neutral. The hydrogen is now with hydroxide. And what you have to remember is that hydrogen and hydroxide mean the same thing as water. And then we balance. Very, very common. If you left it as hydrogen hydroxide, perfectly acceptable, nothing wrong with that. And here's kind of our example we're going to work through. So complete and balance, we've seen this before. Notice here we see 2 ionic compounds. 2 compounds. 2 compounds means double replacement. So I have the hydrogen, I have the calcium. Those are treated as my cations. So the hydrogen is going to be with the hydroxide. The calcium is going to be with the chloride. And when we make those new compounds, we get this HOH or water and calcium chloride. Again, notice the subscripts on the chloride are a Cl2 on the right, right there, and only 1 there. Subscripts on the left have nothing to do with the subscripts on the right. But we have one more step after this. We have to balance, so I balance with coefficients, and everything is peachy. So our last reaction type is combustion reactions. And what this is, it's going to be something reacting with oxygen. That's what combustion means. Something plus oxygen or O2. Commonly, we are going to see light or heat as a product. Now there's a special type of combustion called hydrocarbon combustion, where you have a special type of compound called a hydrocarbon reacting with oxygen. What is a hydrocarbon? A hydrocarbon is a compound containing hydrogen and carbon, and oxygen can often come along to the party as well. Now, if you have complete hydrocarbon combustion, the products will always be water and carbon dioxide. So if you see a hydrocarbon, that's a carbon and hydrogen compound, oxygen can come to the party, plus O2, you know it's hydrocarbon combustion, and the products will be water and carbon dioxide always. Otherwise, it can actually look a lot like a synthesis reaction, very commonly. Now, as a note, if there is not enough oxygen present for complete reaction, instead of carbon dioxide and water, you can get carbon monoxide and water. So just kind of watch out for that. So we always need some examples. So here's an example of magnesium combustion. It's magnesium plus oxygen, therefore it's combustion, and we make magnesium oxide. Again, notice this is actually also a synthesis reaction. So it's synthesis and combustion. But here's an example of hydrocarbon combustion. So I have this compound here, CH3OH. It's carbon, hydrogens, oxygen along, plus oxygen. Products will be carbon dioxide and water. So we're going to look at a example. I want you to work this one out. We're going to do it together. So we have CH4, also known as methane, plus O2. So I recognize it's combustion because it's something plus O2. Secondly, I recognize this is a hydrocarbon because CH4 is called methane. You don't need to know that, but it's made of carbon and hydrogens, so a hydrocarbon. So the products will be carbon dioxide and water. And then we just have to balance it. Okay, so now we're going to look at reactions in aqueous solutions. So again, this means things dissolved in water. These can get kind of messy, and because of this, we often use something called a net ionic equation to do this. And the net ionic equation is a simplified kind of version of the equation that shows really the stuff that's actually changing. It's focusing on the exciting part of the reaction. And what this is taking into consideration that most ionic compounds, and especially the ionic compounds we're going to be dealing with, will break apart into their cations and anions when they're dissolved in water. Now, as a note, these net ionic equation problems will always look like a single or double replacement reaction. Just throwing that out there. And again, we're going to focus on how to generate a net ionic equation because that's actually showing the kind of important parts of the reaction. So we're going to look at an example. Now, first here, notice I've given you the entire equation. That's just going to be for practice. You could and will see a problem on the opportunity where I will simply give you the reactants. You have to figure out the products. Now, the nice thing about this is, again, these are always single or double replacement. So what sort of reaction is this? That's right, this would be a double replacement reaction. Now, what we're going to do is we're going to break this into its ions. Now, the trick of this is that we only break apart the aqueous compounds. Only. If it's a solid, leave it alone. If it's a liquid, leave it alone. Gas, alone. Aqueous, only. And what we're doing is we're just saying what ions are present. We're not concerned with how many there are. So if one of our ions had a subscript of 2, let's say in sodium chloride there was NaCl2. It's not, but we're going to pretend. It would break apart into a sodium ion and just a single chloride ion. Do not focus on how many there are, focus on what they are. So, when I break this apart, this is what I get. The silver nitrate breaks apart into silver and nitrate. The sodium chloride breaks apart into sodium and chloride. The silver chloride stays exactly as is. Why does it stay as is? Because it's a solid, not aqueous. Finally, the sodium nitrate turns into sodium and nitrate. Now, This is pretty ugly right now. This is like those math problems you've probably worked out that it starts off and it gets ugly, it gets way uglier, and then things start to simplify down. That's what's going to happen here. So what we do next is any ion that appears on both sides of the equation exactly the same gets canceled out. We're canceling them out because they're not changing, and a net ionic equation is focusing on what is changing. So I rewrite the equation, and now we see what's the same on both sides. And I can see pretty clearly, is silver the same on both sides? No. I have silver here, silver chloride there. Those are not exactly the same, so I leave alone. But the nitrates though get canceled out. So do the sodiums. Why do they get canceled out? Because they're exactly the same on both sides. Finally, we rewrite what's left, and that is our net ionic equation. So this is saying in this reaction, these are the things that are actually undergoing a change. These are the things that are interesting, and that's what the net ionic equation is all about. Next, any of the ions that we canceled out, those are called your spectator ions. Spectator ions are present, but they're not doing anything. Kind of like, I'm going to be harsh here, you may know at school there are spectator students. They're students who are here, they hang out, but they don't really do anything. So we do need to just recognize that we're canceling out the spectator ions. Those are what we are removing to create our net ionic equation. Now, what we also have to do in writing out net ionic equations is we have to balance out the electrical charges. The last problem did that for us, but I'll show you another example where we have to take care of that ourselves. So here's another example. Again, I've completed this one for you. So first off, we can ask what sort of reaction is this? Well, this would be a single replacement reaction because, again, I have an element and a compound. The lead is kicking out the silver, so the silver is by itself, leaving us with this lead 2 nitrate there. So again, providing this to you for the sake of ease. So first thing we do is we break it apart. Anything that's ionic, we break apart, or aqueous, I mean. So notice the lead stays the same. Silver nitrate turns into silver and nitrate. Solid silver stays the same. Lead nitrate turns into lead and nitrate. Now I really want to focus here and draw your attention to the fact that in the original, this lead nitrate had this subscript of 2 there. We had 2 nitrates. Here, we're only showing 1. That's because in a net ionic equation, when we break it apart, we are focusing on what is present, not how many are present. If we put 2 nitrates there, things start to get funky pretty fast. So make sure you kind of pay attention to that. So we've done that. So we're going to identify our spectator ions and cancel them out. So again, I've just rewritten the equation. You wouldn't have to rewrite this on your own paper. So the lead is different on both sides, so it stays there. Silver is different on both sides, so our only spectator ion in this one is in fact nitrate. So we rewrite what is left. Now, remember I mentioned we have to make sure the charges are the same as well. So notice on the left side of the equation, lead is neutral, silver is a +1. Neutral and +1 gives us +1 total charge on the reactants here. On the product side, silver is neutral, lead's a +2, so we have a +2 charge. Those are not the same. So how do we make this the same? Well, on the left side, where it's only a +1, we need a +2 charge. Only silver has charge, so we're going to need more silver. And again, we're using coefficients for this. So I add a silver there to balance out the charge. Now the silvers themselves aren't balanced, so I have to add a 2 to the silver there. Notice that does not change the charges because the silver on the right is neutral. And this would be your complete balanced net ionic equation. And again, we're really only going to see this with single and double replacement. Okay, now you may have been wondering, then each of these cases we had this solid present. How did I know that certain compounds were solid and others weren't? Well, that's because there's some rules. So again, when we're mixing these together, we're going to get an insoluble product form. Insoluble means solid. We call that insoluble product a precipitate. Precipitates will be a solid. Soluble things are aqueous, insoluble will be solid. So just some vocabulary to watch for. There are rules for predicting if a product is soluble or not. They can get kind of complicated, so I'm going to give you a simplified version of these rules. Again, if it's soluble, it will not form a solid, it will be aqueous. Here are the solubility rules I expect you to know. Compounds that contain ammonium, nitrate, acetate, sodium, or potassium will always be soluble. So if your compound contains one of those ions, it will be soluble, which means it will be aqueous. What if your compound does not contain any of those? Well, then it will be a solid. That's how you tell. So now with this, we can actually complete equations like we've done with in the last section, and then we can balance, and then or not even balance, but we can complete and then do the net ionic equation and balance that.